Hello. I still have no idea how to start videos, but I don't know, maybe I'll figure it out if I ever end up uploading regularly. So, anyway, today I wanted to show you guys an 8-bit computer that I made a couple years ago. I've been thinking about making this video for the past week or so, but last night Ian told me he was like editing a video, and I was like, just out of nowhere, I was like, oh, maybe I'll just make a video. So I was like, screw it, I'm making this video. But anyway, I'm not gonna go super in depth on how this thing works because, like I said, I made this like 2 years ago. I barely even remember how it works myself. I'm just gonna do a brief overview of the layout of the computer, and then I'll make a quick demo program just to show it in action. And just a fair warning, this thing is very, very slow. It is not very good at all. Like, this is if you were expecting this to be a good Minecraft computer, you are definitely going to be disappointed. But anyways, yeah, I'm just gonna fly up so you can see everything in one shot, and then I'll start going over stuff. First, I'll start with the memory since it's the biggest part of the computer. So this is the memory. This giant square holds a whopping 256 bytes of data, and it's almost certainly the slowest part of the whole computer. It basically takes 3 signals, a read, a write, and a set signal. When the read signal is on, it outputs the value of the current byte onto the bus. When the write signal is on, it writes the value on the bus to the current byte. And when the set signal is on, it sets the address of the current byte to whatever is on the bus. So, if you don't know what a bus is, I'll explain it in a minute. But basically, everything you see in light green on the right half of the screen is associated with the memory portion of the computer. The stuff on the left is not actually hooked up to anything. That was just testing, and I never deleted it. Next, since I mentioned it while talking about the memory, I'll talk about the bus. The bus is essentially just a single set of data signals that's connected to every single component in the computer. What it allows the components to do is just send data between each other at like whenever they want. Well, not exactly whenever they want, but you know, each component can put data on or receive data from the bus so they can communicate with each other through that way. And then the bus is just 8 bits, a single byte. So each clock cycle can only send a single byte between components at a time. And every single one of these light blue wires is a piece of the bus. And the bus just basically spans the whole computer, lets everything talk with each other. This little dark blue thing in the corner is a program counter. It's basically just there to keep track of what instruction the computer is currently on. Each time the computer reads an instruction, it'll increment the program counter by 2, since in this computer each instruction is 2 bytes, even though it's an 8-bit computer. 8 bits is not really a lot of information, so I just figured it'd be easier to make it each instruction is 2 bytes. But also the computer can decide that it wants to set the program counter to any value, so if the program needs to jump around in the code, it can do that. The orange bit is the ALU, and if you know a little bit about how processors work, you probably heard of the ALU before. It's basically just where the computer does all its calculations. And in this computer, this ALU only has an adder, which can be configured to subtract, but I got kind of lazy and never actually implemented a subtract instruction, so even though the hardware can subtract, the computer can only add. But yeah. So all this brown section plus all these yellow wires are part of the control unit. The control unit is what decodes each instruction, and then it sends control signals, which the control signals are the yellow wires. The brown part is where most of the control logic is. There is some control logic like down at the bottom here that's on the yellow wires, but it doesn't really matter. It'll decode the instruction and send control signals to each component, so each component can decide what it's going to do in each clock cycle. And then this little blue piece in the control unit is actually another counter. It's used to count sub instructions because each instruction actually takes multiple clock cycles to run. Basically, each instruction takes multiple steps to decode. So that's what this counter is for. It basically just keeps track of which sub instruction is currently on, and then every time it finishes an instruction, that's when it tells the program counter to increment by 1. Well, actually, it reads the instruction, increments the counter by 1, then reads the data, and then increments it by 1 again, because the instructions are set up so the first byte is the instruction operation code, and then the second byte is the data. And then the actual clock is right about here. You can kind of see it. It's just a simple etho hopper clock. But yeah, it's this thing. The signals take a really long time to get to the other end of the computer, so it needs a lot of time. So it only runs about like once every 2 or 3 seconds. So not even 1 hertz. And then right over here, there's all this like red, white, and cyan stuff. That's just some stuff I made recently to make an interface for programming the computer. It makes it easier because before I was like manually flipping levers and like going back and forth, clicking control signals to program the computer. It was a real pain. But basically, it doesn't actually serve as I/O. It's just there for me to read and write the individual bytes in the memory, so I can set them to what they need to be for the program I want. And then lastly, I almost forgot to mention this, but there's also registers, which they're not really any specific color or anything. I'll try to highlight the ones I remember where they are, but I kind of just like stuff them in between the bus and the different components. But basically, they just act as like a temporary like memory location for a single byte. So there's an A register, a B register, an O register, and I think I threw another register in there that's not used for anything, but I don't have any instructions to access it, I don't think, so it's kind of useless. But anyways, the A register is the A input for the ALU, the B register is the B input for the ALU, and the O register is the output of the ALU. Alright, so I'm gonna get to programming this thing. So first off, I will come down here and look at my instruction board. These are all the instructions I made. We've got a no-op, load a value into the A register, or load an address into the A register. Same with the B register, and store A, store B, or wait. Oh, okay, there's no store B. Basically, this will store whatever's in the A register into memory. And then I have a sum, which obviously just takes A and B and adds them together, puts it in the O register. And then this will store whatever's in the O register into a specific byte in memory. This halt will just stop the clock. Jump will jump from one memory location to another. And then this one will just take, instead of taking a direct memory location, it'll jump to whatever location is at the address that's being pointed to. So not very many instructions, but we can do some interesting things with this. So I'll write a simple program that, well, and honestly, there's not much we can do, but demonstrate, I'll just make a program that adds 3 numbers. So first, I guess we'll add the numbers 5, 47, 22. So basically, our program is going to look like this. I'll write some sort of assembly code. Not really, but kind of. Just to demonstrate what the program would look like. So the first instruction is going to be a load A with a 5. Second instruction is going to be a load B with the 47. Then next instruction will be sum, and there's no data for that. You just call it and it does its thing. And then I'll take store O and store it somewhere in memory. Right now we don't know where that is, but I'll get to that. And then we're going to take a load A, and we're going to have some other memory location, the same one as the store O, because what we're doing is we want to take the result of that and put it back into the next sum instruction. So basically what we're doing is we're taking the two numbers, adding them together, and then putting it in a specific location. So what that specific location is going to be obviously depends on what our load A instruction is going to be. So basically this load A instruction, we don't have to give it anything because this next byte is going to be set by the store O instruction. So if we look at the load A, we see that it is going to be called at line 8, or that it's going to be the 8th byte in memory. So basically we want to set the 9th byte in memory to the output of that first add. So we'll set the store O to 9, and then the load A can be whatever, it doesn't matter, just put it 0. And then so now we load the next number, which is 22, into the B register. Then call sum again. And then we'll store that result somewhere just so we can look at it. I'll put it at the very last byte in the memory, which is going to be 255. And then we'll call halt. And so basically, I already have most of this programmed in the computer. I just have to change the numbers mostly, because I wrote this program before just with different numbers. So I will go back to our interface. And the way this works is this is our little buffer. We can set it to whatever. When we hit a button, I'll turn hit F1. Hit a button, it turns the light on, and then if you hit this, it'll clear them all. And then this shows us what address we're currently on. So no lights are on, so that means we're currently on 0. So our first address is going to be a load A. I think I might have cleared this one. Let's see. This thing takes a bit of time to read. Yeah, there's nothing in here. So what we want to do is set it to load A, which if you looked on the board, I have this written down in my notes. They're behind me, so it's kind of awkward. But this instruction is going to just be 1. So we do that. Oh, whoops, I hit the wrong button. Okay, basically that just moved to the first address. So I have to go back. Okay. Now we put the 1 and then do update. That will put it into memory. Okay, it's done. So now if I clear this and I read, you'll see eventually it'll come back with a 1. It takes a minute because this thing isn't very fast. There it is. Okay, so now we want to set our 1 address to, so we want to go to the first go to the 1 address. So it's already 1, so we could just hit that. We'll go to address 1, and then this is going to be the data bit, or byte, sorry, the data byte for our load A instruction. So basically, I mean, I don't remember what's in there. There's something. Okay, it's 15. No, it's not 15. Whatever number that is. I'm not quick at reading binary. But wait, is that not 15? I thought, no, it shouldn't be 15. Oh, 25. Wow, I'm dumb. Okay. Anyways. So, we want this to be a 5, so I'll clear this buffer. And then put in a 5. And then hit update. And just once this light is cleared, that means it's in there. So the rest of the program is loaded except for the numbers, so I'm gonna skip the, I'll just double check just to make sure, but our 2 should be, oh whoops, I messed up. Well, that should give us back a 5. Yeah. Just gonna double check, set the address to 2. Now read what's on 2. It should be load B, which I believe is 2. No, it's 3. And yeah, there's a 3 there already. So I'm just gonna go ahead and skip to address 3. Which there's some number there, I don't remember what it is, but I want to put in a 47. So 47 is going to be 32 plus 4 plus 1? Oh, that's 37. 32, 40, 5, 4, 47, right? I'm just gonna double check this. I have an app on my phone, or actually, it is 101111. Okay, there should be an extra 1. Yeah. Okay. So we're on address 3, I'll set that. Takes a minute. Now, the store 09, since it's the same program as before, it should already be to the right address. I'll just so you guys don't think I don't know. So it doesn't seem like it's fake or whatever. I'll go to the next load A instruction, which was at 8. So I need to set address 9. Alright, it doesn't need to be set to anything, but it will be set to something. Probably the result of whatever I ran last time. Yep. So I'll just set it to 0 just for the record. Finish rate. Okay. And then wait, let me just double check. I just spaced out for a second. Yeah, okay, now we're gonna go to 11 because that is our load B, or the data bit of our load B, I should say. Okay, and then I will set it to 22, 16, 20, 22. Date. Okay. Now, just to show you guys, I will set the last bit to 0. So we're gonna move over to the very last bit, or byte, sorry. Keep saying bit, I mean byte. And then I'll just read it just so we can see it's a number. Or actually, I think I cleared it already. And there, yeah, see, it's set to 0 already. So now we can run the computer. So I haven't really made a proper reset, but I have a few buttons I have to click to properly reset the computer. Set the program counter to 0. Make sure this counter is on 0. And then we can start the computer. So as you can see, it's a very slow clock. It's several seconds per clock cycle. So that's what, 16 instructions I think in the whole program. And you saw how slow that goes, so it's gonna be a while. I'll speed it up. Here you can see this will keep track of what the last memory location is read. So if you want to just like, I'm not gonna like go over what's happening, but if you want to watch it and see what's happening, you can do that. I'm not gonna explain it, but you'll be able to see what's happening. So yeah, I'll be back in a couple minutes or whatever, how long it takes. Okay, well I was gone for a while, so I don't actually know quite how long that took. But as you can see, it's on address 16, which was the last address in, or the last instruction was on line 16, so that should make sense. And then if we go over here, we can see this is an 8. It's left to right, or least significant and most significant. This would be bit 8. And this is like the instruction. Well, it's just the instruction. So the 8 instruction is a halt, as you can see. So it stopped, and then you can see the clock has stopped. It is no longer flowing. And I could hit this and start it again, but that wouldn't really matter. So now for the moment we've all been waiting for. Did it give us the correct answer? So if you remember, I programmed it to set the very last bit, or put the result in the very last bit, which is all the lights on. Set the address, and then read the address. So the numbers we added together were 5, 47, and 22. So if I add those together on my calculator, that should be 74, which is 01001010, which is what it says. So I hope someone found this interesting, even though this isn't the most impressive Minecraft computer out there. I thought it was pretty fun to build, and I think it's cool, even though it's not very good. But anyway, yeah, if you made it this far, thanks for watching. Yeah, if you guys want me to do more things like this, I could try to start uploading more, but I don't really know. I'm not really good at coming up with ideas for things. The only other idea I'd have is making like a 32-bit computer and making videos on the whole process, but I don't know. I don't know how popular this kind of stuff is, so if people like it, I'll do it. But anyway, that's all. Bye.